beautiful, massive, magnificent. Today, airplanes have become some sort of gracious monsters. And the more massive they are, the more intense their wake vortices. Except in rare weather conditions like these, you generally don't see wake vortices. And that's a problem. The vortices induce these large perturbation velocities on their surroundings, so they can be dangerous. Imagine there is another airplane flying nearby. Well, if it really flies into the vortices, it can easily lose control, so this is really a major safety concern. Today, wake vortices are also the main constraint that imposes a separation between airplanes that land on the same runway. We want to study the vortices to determine their physical characteristics so that we can better predict them, avoid these dangerous wake vortex encounters, and better control the stream of airplanes that land at busy airports. Another area of interest for wake vortices is formation flight. By allowing an airplane to fly not inside a vortex but right next to it, you make it benefit from the upward velocity induced by the vortex. So an airplane that flies in formation like this will experience less drag and therefore will consume less fuel. It's exactly what migrating birds do when they fly in these V-shaped formations. They are saving energy. And in fact, birds, helicopters, airplanes, they all produce a pair of vortices. So one question we can ask, and that I tried to answer with my thesis, is how similar are these wake vortices? Is there some sort of universality in wake vortices? Now, the problem is, how do you address a question like that in a tractable way? We're talking about very high Reynolds numbers, but also we want to track the quantities of interest over long distances. And this makes the problem even more difficult to study with regular experimental methods or using computational fluid dynamics. So my thesis has focused on advancing a numerical technique called the vortex particle mesh method to simulate these space-developing wakes. The vortex particle mesh method, or VPM for short, works with the vortice velocity formulation of the Navier-Stokes equations. We discretize the flow using particles so that each of them carries a certain amount of vorticity and has a certain velocity that we compute using the Biot-Savart law. The advection is solved in a Lagrangian way simply by integrating the position of the particles over time. The originality of the method lies in the addition of a background mesh. We use it to compute the right-hand side of the Navier-Stokes equations with higher-order finite differences, and to solve the Poisson equation that arises from the Biot-Savart law. This operation is by far the most computationally intensive, so one important step in this work was to improve its efficiency. Therefore, we have developed a new open-source library called FLUPS. The resulting method combines the advantages of a Lagrangian method with relatively low dissipation and dispersion errors, while it benefits from the implementation on a grid that helps accelerate the computations. To model the presence of a wing, we developed the immersed lifting and dragging line model. Similarly to actuator methods, it captures the effect of the lift and the drag forces, but in a way that is compatible with the particle approach. The lift is related to the concept of circulation, that is, the integral of the vorticity in the boundary layers. In a viscous fluid, these boundary layers developed around the airfoil and eventually separate such that the vorticity is transported in the wake and creates a velocity deficit. This constitutes the signature of the parasitic drag of the airfoil. The idea behind the model is to replace the airfoil by the combination of a vortex monopole that accounts for the lift and a vortex dipole that takes care of the drag. Consistently with the VPM method, the vorticity in the wake is discretized with particles so that we maintain the Lagrangian properties of the whole method. In 3 dimensions, we use several of these discrete vortex elements to form a line that effectively replaces a wing. In the end, the particles in the wake naturally roll up, which leads to the emergence of the wake vortices, plus any subsequent interactions or instabilities. With this new simulation tool, we were able to study how the vortices are formed in the wake of different types of aircraft. Here, we simulated the flow behind an elliptical wing and past a helicopter rotor in advancing flight. What's really unique in each of these cases is that we capture the wake development as a function of space and time over a distance of 30 spans. And that's great because these results give a lot of information about the transition region between the near wake and the far wake, and what happens in that region is critical to determine the characteristics of the wake vortices. For instance, we have discovered a relation between the phenomenon of wake wandering in the far wake and an oscillation of the vortex sheet that appears much closer to the wing. These oscillations are due to the airfoil parasitic drag and the related velocity deficit. So for the first time, we have determined that when they propagate downstream, these oscillations interact with the wake roll-up process and finally give rise to the wake wandering. Helicopter wakes also present various specificities. In this case, the near wake is highly three-dimensional and dominated by the tip vortices. We found that it is primarily the action of vortex dynamics through many vortex mergers and reconnections that align the vorticity in a principal direction. So after the development of the wake, we obtained two parallel vortices surrounded with turbulence. Finally, by comparing these wakes, we found that helicopter vortices generally have a larger core than airplane vortices. So wake vortices are universal features of lifting bodies, but their internal characteristics depend on their generation process. Besides the characterization of wake vortices, I think my thesis has brought original contributions to the modeling and post-processing methods that are required in these simulations. Wake computations can be prohibitive because they require at the same time large computational domains and relatively high resolutions. Here, we have seen that actuator methods drastically reduce the computational requirements while they retain the meaningful physics. Software-wise, it's also key to work with a code that is optimized for parallel computation on a supercomputer. During my thesis, I've been able to improve the VPM code with the new FLUPS library, which speeded up the execution roughly by a factor of 2. What I really like in this research is that it touches two different aspects of engineering. The first one is the industrial aspect with the issues related to landing separation minima, wake vortex encounters, and formation flight. And the second aspect is much more fundamental. Studying wake vortices and related phenomena is a proxy to approach deeper questions in fluid mechanics about turbulence, instabilities, vortex interactions. In the end, what are the mechanisms that drive the coherence in a flow? And these questions are quite relevant regarding our general understanding of fluid mechanics. Now I work at BYU as a postdoc. We pursue several research activities in the lab. One is related to urban air mobility and the design of these new vehicles that are becoming popular. In this regard, my thesis works have paved the way for a better understanding of the wakes of such rotary vehicles, and I hope this will help prevent accidents in tomorrow's cities. I'm also currently working on wind turbine optimization. We are especially focused on floating offshore turbines, and this is really challenging because of the multiphysics aspects. You need to account for the waves, the motion of the platform, and the coupling with structures and aerodynamics. Here again, we see that vortex methods are powerful and efficient in such an unsteady framework. Renewable energy is really a key to mitigate the effect of climate change, so I'm really excited about this research as I believe it can have a positive impact for us all.